So today's first session is going to be summary and discussion, finding young planets with direct imaging, precision radial velocities, astrometry, and transits. So these are summaries of full talks that are online. Each speaker is going to have 10 to 12 minutes to summarize it, and then we'll have a nice discussion session at the end. So I think there isn't a specific order, but probably easiest to go by the list of speakers on the website that in the order is given. So we'll start with Anne-Marie Lagrange, followed by Arpita Roy, Matthias Novak, and Andrew Mann. So Anne-Marie, do you want to share any slides you have?
Yeah, sure. Hello, everybody. Thanks to the organizer for inviting me to this meeting to talk about direct imaging of young planets. I will talk direct imaging from the ground, and the full talk is available on the YouTube. First, why do we want to do direct imaging, as there are already 4,000 planets detected, mainly with indirect methods? In fact, as you see here in this diagram, the indirect methods allow you to detect planets up to the border of the outer solar system. But if you look at the other giant planets, they are out of reach of indirect methods. So we want to, if we want, for instance, to observe solar-like systems, analogs, we have to do direct imaging. We want to fully explore the architectures of the system, and we want to do planet demographics. Using direct imaging, you can also study the planet properties, effective temperature, gravity. If you add spectroscopy, you will access the chemical composition of the planet, of the atmosphere. You will access the radial velocity, maybe the rotation period. So a lot of things to do with direct imaging. Of course, it is also a very exquisite way to study disk and planet interactions and formation processes, as I will show later. Why young planets? If you look at the contrast between Jupiter and the Sun today, it's about 10 to the minus 9 at 2 microns. So it's a very huge contrast to compare to what we can do today. But if you look at the model, tell you that the same Jupiter, when it was 10 million years, was 1,000 times brighter. And this gives you a contrast ratio of about 10 to the minus 6, which is something that we can deal with, actually. So this is the reason why we look at young planets. And we are lucky enough to have several young associations very close to the Sun, at less than 100 parsecs, let's say, or at a little bit more. Close young associations, star-forming regions. So there are plenty of objects to look at in this regime, let's say, younger than 100 megayear. Okay. To do that, to do this direct imaging images, you need to, there are 3 key steps. First, you need to correct the incoming wavefronts from the perturbation that has been that is done by the Earth's atmosphere. The Earth will perturb the incoming wavefronts that arrives flat, and then it will be turbulent, and then you have to analyze and to correct optically this perturbed wavefront to retrieve a flat wavefront so as to get a proper, what we call point spread function and airy pattern. To show that, to illustrate that, you have here the image of a star that a normal star observed at the VLT in the H band under seeing limited conditions. So you see that the image is totally blurred, and if you use the adaptive optics, in this case the sphere system, you concentrate the light of the star into the airy core, and you of course you get a much better contrast. You will be able to detect much fainter objects close to the star. Here the contrast is about 10 to the minus 3 at 0.5 arc second from the star. This is not enough to detect planets. You have to add coronagraph to block the star light, and then you win another 10 factor of 10 in contrast. And then you have to use data processing tools to remove the speckle that remain in the halo of the star. And with adding up these three steps, you get a contrast. You can reach a contrast of 10 to the minus 6, which is kind of the magic numbers that you need to start to do something with indirect imaging. The first, from an historical point of view, the first detection of a planetary mass object close to to stars other than the sun were done in back 15 years ago with NACO, which was the first adaptive optic system mounted on the VLT for all astronomical purposes. This is here a planet or body that is at the limit of the in mass between planets and brown dwarf, and it is located at more than 200 astronomical units from the star. Here you have a planetary mass object, about 5 Jupiter masses, orbiting a brown dwarf. And these two objects, of course, raise the question how they were formed. Since this early detection, there was another step. The next step was back in the 2010-ish with the image, the first image of a planetary system around HR 8799 with the companion B at 60 astronomical unit, 40 for companion C, and 24 for companion D in projected separation to the star. And there was also, by Christian Marois and collaborator, and there was also the detection of a Beta Pictoris B, which is a planet here, which is seen here back in 2003 at 9 astronomical units from the star, and that we reobserved a few years later at about, in projected separation, 6 or so astronomical units. With this instrument, Niki at Gemini, NACO, and at VLT and other instruments, a few planetary mass objects were detected. And as the technique was successful, it was soon realized that we needed to improve still the performances of the adaptive optic system. And it was done with on a number of instruments. In particular, there was the GPI instrument that was built dedicated to the search for planets, and the sphere instrument on the VLT, GPI on Gemini. Both instruments have what we call extreme adaptive optic system that analyze and correct very rapidly the perturbation of the incoming wavefront. Yesterday, Eric Nelson told about the result of the sphere and GPI surveys. These both instruments have observed about a few hundred of stars of all spectral types in the nearby associations that I mentioned earlier in this talk, plus in the SCOSEN association that we will talk about again. And half of the data have been analyzed and published so far. Even so, the survey are ended. The main information to keep in mind is that there is the sensitivity with respect to previous generation of instruments has increased a lot. And you have here the compared sensitivity in terms of probability of detection in red with the first generation of instrument NACO on the VLT, and with the second generation with sphere on the VLT. You see that we are able to detect lighter planet closer to the star, and this is what we wanted. You see that the sweet spot of the detection now, both with sphere and GPI, is for planets further beyond the 10 to 20 astronomical units and masses of Jupiter, planets more massive than 3 to 5 Jupiter masses, which is still show you that we are not still reaching the 5 to 10 astronomical unit region. Planets were detected, 6 planets in total were detected by GPI or sphere. GPI detected 1 planet around 51 Eri, and this planet is very cool because, well, it's cold, it's 600 or 700 K, and it was detected through its absorption in the methane in the methane line, showing that there is methane absorption, and it was like that the planet was detected here. The first planet detected by sphere was HIP 65426, and it was detected further away at 90 astronomical unit, but on a much further star much further away in the Scosen association. And in fact, since then, SPHERE has detected several planets in the Scosen association, and it's really probably now the greatest place to look at to search for planets and disks. And one of these planets is PDS-70b that you see here, that was detected 3 years ago. And it was also observed in H alpha with MUSE, showing that material is, the star is still accreting, the planet is still accreting material. Another planet, PDS-C, was detected, and the system was observed. And you see here this disk, which is a protoplanetary disk. Here we are talking about a system where the disk is really protoplanetary, is very young. And we heard a few days ago about the possibilities that the inner cavity could have been swept up by the planets that we see here, or maybe additional planets. And the observations with ALMA here showed that there is a circumstellar, circumplanetary dust associated to these planets. And earlier today, there was this press release by ESO showing that there is a disk, a circumplanetary disk around PDS-C. So you see here, this is a perfect example of what you can do combining a direct imaging of planets with disk. There is really a lot to do in that field. Three other planets were detected with SPHERE in the Scosen association, and in particular, a small planetary system with 2 planets around a solar type star, whereas most of the planets that we detected before were around A-type stars. And you see here planets that are very remote compared to with respect to the star. And it, of course, you can ask how they were formed. Concerning the statistical results, you had a full talk yesterday on that. The main thing to keep in mind is that massive planets beyond 10 AU are rare. Brown dwarfs are very rare. The distribution of a giant planet and BD brown dwarf follow different distributions, so probably they were formed differently. And you tend to find more massive giant planets around more massive stars than around less massive stars. Okay, now I want to spend a few minutes talking about what I think will be what will be done very abundantly in the next coming years about coupling direct imaging with other techniques to make a characterization of the orbits, of the mass, and to search for additional planets. There is also, of course, a very important subject with this to couple with spectroscopy to do atmospheric characterization, but there are talks about that in the coming minutes. Orbital parameters, of course, are the main parameters that you want to get once you have detected your planet. Of course, as we are talking about long distance, long period planets, it's difficult to follow, to monitor the planet around one full orbit. We can do that mainly only on beta peak for the moment, beta peak B. And you see here the example of possible orbits that you have with a PDS-70b using only direct imaging data. If you couple now with long baseline interferometry, and this was done with gravity, the instrument at the VLTI gravity at K-band, gravity will give you very precise position measurement of the planet compared to the star, with respect to the star. And this allows you to get really, really precise orbital parameter determination of your planets, even though you have not monitored the planet all along its orbit. Another important question is the mass determination, and you can determine the mass derived from direct imaging are model dependent and are age dependent, because the flux depends on the age. So you need to get dynamical mass measurements. One possibility is to use absolute astrometry given by Gaia and combining with Hipparchus, and it really helps a lot. For instance, in the case of the HR 8799 system, when it was discovered, there was a quite large error bars uncertainty on the masses of the planet because the mass of the system was not precisely known. Now, using the early DR3 Gaia data, Brandt et al. Could measure the mass of HR 8799E with a really good precision. You can also measure the masses using radial velocity, of course, and this has been done a lot of times, combining direct imaging and radial velocity for brown dwarf. For exoplanets, it's difficult because you have to have close by exoplanets, and we did some observations with, we combine the direct imaging observation of beta peak, all the data that we had gathered since 2003 of the system. So the planet has done almost its full orbit. And we coupled that with radial velocity data. And this radial velocity data allowed us to show that there is another planet inside the beta peak system orbiting at about 3 astronomical units. Combining all the data, the astrometric position given by a sphere and a long baseline interferometry, gravity, and combining the radial velocity data, we could exquisitely constrain the orbit of both planet B and C, constrain the mass of planet C, and still put constraints on the mass of planet B. But for the mass of planet B, if we want really to be sure, we need to have more hard data. But again, this is something that this shows you the real power of coupling high contrast imaging with other techniques. Again, coupling with other techniques, you can you can look for additional planets and put set upper limits to the abundance of to the mass of the planets. And here, for instance, in the case of beta peak, combining the direct imaging and the radial velocity data, you see here the planet C, we can rule out now any planet more massive than 2.5 Jupiter mass throughout the disk, from a fraction of astronomical unit to 100 of astronomical unit. And this shows you the power of the technique. You can also look for additional planets using Gaia, and this was done by Brandt et al. Earlier this year, combining the direct imaging data, astrometric data, and Gaia, EDR3 data to rule out a planet more massive than, let's say, about 5 or 6 Jupiter masses at distances of about 5 astronomical units, and this gives you the span of the debris disk that is around the planet. So we are starting to really to see to give really interesting upper limits in mass to the possible planet that creates the disks. Current limitation of today high contrast imaging, we are still limited in terms of semi-major axis and mass range in the detection capability that you see here. We are sensitive also to young planet only. So if we want to do better, we have to be sensitive to lighter planets, and we have to be sensitive to planets closer to the star. And I remind you here that we are comparing very young planets to old planets. So it's we have always to be cautious when we compare, when we look at this type of diagram. In order to go, we have to go deeper and fainter in high contrast imaging to access closer planets and lighter planets, and we have to improve data processing. There is a lot of margin of improvement, I guess, in data processing. The parent star and this will also help, of course, to detect older planets. We are still limited in the magnitude of the planets, of the stars that we can access to, and so we want to improve the wavefront sensor capabilities in order to be able to observe fainter stars. And also, if we want to better characterize the planets, we have to go beyond the current limits, let's say 50 power in terms of power of resolving power in spectroscopy. We need to couple with higher resolution spectroscopic data, and this is hopefully will be possible hopefully in the next year with the sphere plus with the upgrade of the sphere instrument and the upgrade of the GPI instrument. The first one will be available in 2025, something like that. GPI will come in 2 phases, and the first phases should be next year. And there are also some other improvements on other instruments that are scheduled. I will finish now with the next step, which will be, of course, the extremely large telescope, which will be used to detect and to characterize planets. And in some cases, it will be very intimately mixed. And the idea is to detect planets down to super Earth mass planets or Earth mass planets. And I will leave you with this last slide about the first generation instrument on the ELT, Mikado, Harmony, and Métis. And I show here the contrast that we hope to get with these instruments. And some illustration of what we will be able to do with this instrument. Basically, with the first one coming very closer to much closer to the star and observing lighter planets, and with Métis, which will be observing in the mid-infrared, being able maybe to observe planetary mass, Earth mass planets around Alpha Centauri. And there will be several talks about that tomorrow, I guess. And so now I thank you for your attention.
All right, so I think we're going to hold questions until the end. So we'll move on to our next speaker. So just to note, I will be giving you verbal, I'll let you know when you have 2 minutes left for the rest of the speakers. So next speakers are Pita Roy. If you want to take over.
Thanks, Beth. Can you guys see my screen? Okay, great. Hi, everyone. It's great to be here talking to so many of you from around the world. I'm going to talk to you about finding young planets with precision radial velocities. Some of you might have heard of this technique. It's actually the technique that found the very first exoplanets. And I'm going to introduce some terminology here, which is the term EPRV, which is a relatively new phrase that we've come up with, which stands for extreme precision radial velocity. And that word extreme there signifies going from the original instruments that were finding planets at about the meter per second level or higher precision, less precision, to moving towards trying to find planets at the 10 centimeter per second level, which is the signature that our Earth imposes on our sun. So let's talk a little bit about the fundamental concept of the radial velocity technique. The main idea here is that both the planet and the star are orbiting a common center of mass. So the presence of the planet has an influence on the star. And so while we cannot see the planet directly in this method, indirectly, we see its gravitational impact on the star. So as both the star and the planet orbit, the planet has this large orbit because it has a small mass, and the star has a large mass, so it only has a small orbit. And so we call that the wobble of the star. As the star wobbles, it moves away from us and towards us, and the light gets Doppler shifted in response, red and blue. And if we measure that over time, we can measure directly the period of the perturbation, which tells us about the mass of the planet. Now, this is very challenging to do at the 10 centimeter per second level. For reference, 10 centimeters per second is about the speed that a tortoise walks. So this is a pretty slow speed that we're trying to measure, and these stars are light years away. So this is very challenging technologically. However, the exoplanet community has sort of risen to meet this challenge. And so in the last few years and in the coming few years, there are 23 new ground-based RV spectrographs that are being commissioned at observatories around the world. And so in this timeline, I'm showing you those 23 instruments with their goal precisions, as well as some of the space missions that are launching along this timeline that have relevance to exoplanet studies. So this is really kind of an army of new technology that is coming online to try to meet the huge demand for these instruments, since there are so many interesting planets to study. We are still, even with all of these instruments, we are still resource limited in measuring the masses of the planets out there. So the good news is that we've been building these instruments, we've been producing data. And so let me tell you a little bit about how we measure extreme precision radial velocities from the spectra, because this will have relevance as we talk about young stars in particular. So we collect the spectra and we extract the spectra, we correct it for all of the systematics that occur due to the observatory, due to the fact that we are located on Earth and have to look through Earth's atmosphere, and the Earth itself is moving around the sun. And we also try to correct for stellar physics that might be in the data. But after those corrections, we want to measure the radial velocity from the spectrum. And the way we do it, this is kind of a simple cartoon showing how we do it, is with cross correlation with a stellar mask. There are a few different ways to measure radial velocities, but this one seems to be the most robust as yet. And so the principle underlying this measurement is that true bulk motion of the star, where the star is actually moving in space, causes all of the stellar lines to move in an identical way without changing shape. Whereas something like stellar activity or contamination or something between you and the star that is messing with your spectrum will often have a chromatic behavior. So we take our stellar spectrum, shown here on the left in white, and we construct a mask of all of the lines that we think are best for measuring radial velocity. So we pick lines that are clean from stellar activity, that avoid telluric regions, and we pass that mask basically across the spectrum, building up a cross-correlation function that you see in the middle. This cross-correlation function looks very much like an average spectral line. And then we fit it usually with a Gaussian, and the centroid of that Gaussian gives us the measurement of that epoch of radial velocity. We actually do a slightly more sophisticated things like measuring this across different wavelengths and correcting this for different effects. But essentially, this works really well for sun-like stars that have well-defined lines, and you can pick out the nice clean lines and still have several thousand lines to measure. However, this becomes harder for stars like M dwarfs, where the lines aren't well-defined and the continuum itself is maybe not present. I'll also say that these masks, the lines that you use to measure radial velocity, can evolve over time as your understanding of that particular system or stars in general gets better. Okay, so we've been building these instruments and delivering them to the observatories. This is a little animation showing NUID during commissioning actually on the WIND telescope. And the good news is that these instruments that are kind of an order of magnitude better than the last generation are actually achieving their predicted precisions on sky. So they're living up to the promise and delivering really beautiful spectra and precise radial velocities. However, the bad news is that now we are limited by noise sources that used to be a little bit below our threshold. And so now we're limited by the star. As our instrument capabilities have gotten better, what we really see now better is the noise from the star, which is not well understood at these levels of precision. So real stars have real problems, and let's talk a little bit about what those problems are and how they affect our ability to detect small planets. This is a graphic I made to show the different kinds of stellar activity. It's sort of a shorthand for the things you should worry about and the timescales on which you should worry about them. And you'll see basically that all of these are above the 10 centimeters per second level, except for gravitational redshift. And so if I put Earth on this map, you'll see that most of these stellar activity signals are larger than the signal you would get from a terrestrial planet that's kind of in the habitable zone. And so if you want to find those Earth-like planets in your data, you have to contend with all of these other signals. And ideally, you want to remove them so that you can believe the planet that is left in the data. You'll notice that these phenomena occur on different time scales. And so you have to sample all of these different time scales to try to see those patterns. And to complicate things even a little bit more, these are not always consistent over time. So for example, spots appear and disappear on the star. And so depending on when you observe the star, the stellar activity pattern will change. So young stars, it turns out, have more problems. This is why the radial velocity field has so far been mostly focused on sun-like stars, which are a little bit more mature. And Anne-Marie showed how for imaging, actually, the young planets are better. They do better with direct imaging, but the stars that host these planets, the young stars, are not easy targets for radial velocity. And so historically, RV surveys have just avoided these stars. But with the new generation of instruments, we're asking, what can we do for younger systems as well? And so there's a few reasons these stars are so difficult with radial velocity. The first is that they tend to be fast rotators, and the way we get precision with spectra depends on the slopes of those spectral lines. So deeper, sharper lines have more information content. For these stars, these lines tend to be blended out, and so the precision that you can get to is intrinsically limited on these fast rotators. Also, a lot of what I showed you before, fitting a Gaussian to the lines, some of these assumptions of nice Gaussian lines breaks down in these stars with very strong magnetic fields. But the main problem is that these stars are more active. So they have higher, stronger magnetic fields. And as a result, when you look at the radial velocity data, you're dominated by stellar jitter, so noise from the star, up to several kilometers per second potentially. And so as a result, if there are small planets or even medium-sized planets around the star, they are hidden in the noise from the star. And so in the past, there have been several false positive detections around young stars, which makes people a little bit hesitant to study these stars with radial velocity. However, we should still target these young systems with radial velocity, and here's why. So this gives us a tool to distinguish between different planet formation theories. You've been hearing about planet formation and some of the gaps in the field in our understanding. And one of the best ways to fill those gaps is with observations. And so different migration pathways operate on different characteristic timescales. And so if you were able to observe these young systems and see them before and after migration, you might be able to constrain which migration timescales are favored and which migration mechanisms are therefore more robust. And so in combination with direct imaging, this would help us see these exosolar systems better in terms of separation from the host star, so you could see planets both close in and farther out, and over time.
2 minutes.
Okay, so a few tools that we have now, even though this is a very challenging task with the new instruments that we're building. So the good news is that even though we have a lot of stellar noise, now we have very high fidelity spectra that helps us characterize that noise as signals rather than trying to kind of average over it as noise. So a few things you can do. One is you can go to the near infrared. This is something we've done for mature stars as well, but turns out that it holds for young stars also where jitter is reduced in the near infrared. You can also look at chromatic radial velocities, so not just the near infrared, but look at the optical and the near infrared together, because if you see a signal in one and not in the other, that tells you something about the star. And the cool thing is with instruments like NUID that are coming online that have broad band passes going from something like 380 to 930 nanometers, you actually have a lot of wavelength range to play with. And the precision is so high that individual NUID orders, so chunks of about 100 nanometers, are at about 1 meter per second precision. So this is the precision that whole instruments used to be at in the last generation. And now we can chunk up the wavelength with that precision. You can also think about treating all lines as activity indicators and trying to classify them as with behaviors that move better with known activity indicators, because really at this level of stability, because there is almost no instrumental counterpart to it, you can trust that any variability you see is probably coming from the star, and it can kind of help you reconstruct what's happening in the stellar atmosphere. I won't go into this in too much detail, but if you look at the literature for young stars with RVs, you'll see some of these terms coming up. Spectropolarimetry is a very powerful tool. There are software tools you can use, and then there are interesting lines you can look at to look for particular behaviors that are happening in the planet. Really quickly at the end, we talked about all the challenges, but this field is starting to have some successes. There's only a handful of planets that have been found with RV searches. I won't go over them. Suffice to say, some of them are already being challenged, but there are multiple promising surveys underway with instruments like HARPS and HPF and SOFI, and NUID also has quite a few geo programs coming up to look at young stars. And I'll end with this closing thought that new fields need new researchers. This is sort of a brand new field that has brand new instruments and is really ripe for developing new techniques, analytical methods, etc. And so if you're interested in this, you should certainly get involved. We are quickly becoming overwhelmed by data, which is a nice place to be, but there's lots to look at right now. And with that, I'll stop and hand it back to Beth.
Great, thanks for an awesome talk. And everyone, remember there are longer versions of these talks online. So also a reminder, put your questions in the Q&A. We're going to go through the last two summaries of the session, but then hopefully we'll have some time for a Q&A session as well. So on that note, we're going to move on to Matthias Novak's talk. And as a reminder, I will give you a 2-minute warning, 2 minutes before you need to stop.
Okay, so let me share my screen. Okay, does that work?
Yep, looks good.
Okay, yeah. So, I'm glad to be a member of this panel to discuss some of the challenges of finding young planets, and I'll be focusing on astrometry. So in the pre-recorded version of my talk, I went quite extensively through the methods and the techniques and how you actually use astrometry to find planets, not only young planets, but planets in general. In this talk, in this summary, I won't go through the details of this. I want to give a broader picture to talk about some of the challenges and some of the possible future developments in that field. But first off, I should probably say that the main and almost the only one actually method which is currently used to find planets with astrometry is the combination of Hipparchus and Gaia data. And the basic idea, the basic principle is to look at the difference between the long-term proper motion of a star, which you get from the difference of position between the two epochs, between the two missions, and the instantaneous proper motion, which you have at the Gaia epoch by the Gaia mission and at the Hipparchus epoch by the Hipparchus mission. And if you have a difference between the instantaneous proper motion and the long-term proper motion, it means that there is an acceleration of the star. And if there is an acceleration of the star, then it's probably that there is a companion around that star. So this is something which has been done on the DR2 catalog of Gaia, for example, by Pierre Cavella and colleagues in 2019. And this is the histogram of the companion candidates found around the stars of the catalog, so combining Gaia, DR2, and Hipparchus. And this is a zoom on the range of planetary masses. So depending on the confidence level you want to use, you typically have something like 100 or 1,000 planet candidates in the Gaia DR2 catalog. This is an example of what you get on an individual target, so in this case, Proxima. So if you find a proper motion anomaly around the star, it means that there is a companion, and you can get an idea of the mass of the companion depending on its separation from the star. And you get something like this plot here, which is interesting in this case because the proper motion anomaly around Proxima cannot be explained by Proxima b. So you need something else in the system to explain this. So that's the first way you can use astrometry to find planets. Another tool you can use is long baseline interferometry, and that's probably the part I'm more familiar with. So for example, using gravity, a beam combiner on the Very Large Telescope Interferometer, so using the 4 telescopes of the VLT Observatory. So it's an instrument we've been using for about 2 years now to characterize young giant planets. So we've demonstrated that this was a powerful tool to get medium resolution K-band spectroscopy, to get high precision astrometry on young giant planets, also to directly detect RV planets such as Beta Pictoris C. It has some limitations, mainly the fact that the field of view of the instrument is limited by the use of a single mode fiber to about 60 milliarcsecond, which means that it's very difficult to use the instrument to search directly for planets. It's almost impossible actually to use this instrument like this. What you can do though is to do an indirect search for planets. For example, basically looking at the astrometry of a star using the high precision astrometry of the instrument and trying to detect the reflex motion of a star induced by a planet orbiting around it. Now, the problem we have with this instrument as it is it cannot measure absolute astrometry. It only measures the astrometry of a star relative to another star, another target. And this reference point cannot be more than 2 arcseconds away from your target of interest, which means that, for example, if you want to look for planets around Alpha Centauri A or B, then you'll need to find another star in the background that you can use as a reference point, and it needs to be at most 2 arcseconds away and bright enough to be used as a reference. So this is a picture I took from a paper by Pierre Cavella, where you see the trajectory of the 2 stars on the sky, and in the background you have a number of stars which are highlighted here, which can be used for such a study. But this means that you can only get the astrometry of those stars at a particular time when you have a close conjunction. So it's quite difficult actually to do a proper search for planets this way. It will be easier with an upcoming update of the instrument, which will raise this limit to 30 arcseconds, but for the time being, it's difficult. So something you can do instead is search for planets around binary stars. And if you have a binary star, then you have an obvious reference point, let's say, to use. You can simply measure the relative astrometry between the 2 components of a star. And then using the high precision astrometry, you could search for deviation from Keplerian motion. This is also something you can do using known planetary systems. If you have a system in which you have already detected planets, such as HR 8799 system, then you could monitor the astrometry of a planet in the system and try to look for a deviation from the purely 2-body Keplerian motion. So this is something which, we are currently doing. It's a work led by Sylvain Snacourt on the Beta-Pic system. So basically trying to infer the presence of Beta-Pic C, which is a known planet, but using only the gravity astrometry on Beta-Pic B. The idea is you use the high precision astrometry on Beta-Pic B. You basically, if you fit a 2-body Keplerian motion and you look at the residual, you can see the signature of Beta-Pic C on those residuals. So all of this is preliminary results, but it seems that it could be doable to look for additional planets in known planetary system with the high precision gravity astrometry. Now, I want to take a little bit of a step back here and talk about why is this useful? I mean, all those fancy ways of finding planets with astrometry, what do they bring to our understanding of planets and planetary formation processes? And Anne-Marie talked a little bit about this in her presentation, which is that it's actually, I think, the most interesting part is this mass luminosity diagram, which is a tool we've been trying to use for years and years and years to characterize the evolutionary tracks of young planets and then relate this to the formation processes. But from an observational standpoint, it's actually very difficult to measure both the mass and the luminosity. The luminosity is usually measured, well, not usually, it's always measured through direct techniques, which work on young targets, on young planets, so around young stars. And we've seen just before that it's actually very difficult to use radial velocity, which so far has been the main method to determine the mass of planets on those young stars. which makes it very difficult to fill out the mass luminosity diagram. Now, the interesting bit about astrometry is that it's sensitive to the mass of the planets, and it's not really bothered by the age of the star. You can use astrometry on old or young stars. It doesn't really make too much of a difference. So in principle, combining astrometry and direct imaging or direct methods in general is a very good way to fill out the mass luminosity diagram. Now, the problem is, it turns out that the direct imaging doesn't quite have the resolution. I mean, it's hard to go to the separations where you can have the Gaia planets. So in principle, it would seem that interferometry, which does a little bit better closer to the star, would be a more useful tool for this. Now, the problem with something like gravity is, again, the field of view. It's not enough to know that there is a Gaia candidate around the star and go, so you have an idea of the mass, and then you go with gravity to look for the luminosity. If you don't know where the planet is, then you can't use this instrument to observe the planet. Which brings the question how we can actually determine the location of those Gaia planets found with astrometry. And I think there are a couple of different ways. One of them is so this is an illustration I took from a paper by James Camera on HD 206893. There is another example by Pierre Cavella on Proxima. So to combine astrometry with other methods, so radial velocity or possibly direct imaging if you're looking at a multiplanetary system, to try to constrain the orbit of the undetected Gaia candidates and determine what could be its location on the sky. Another method using purely astrometric method would be to follow up on Gaia candidates with something like gravity. So it would be difficult actually to set up an astrometric search for planets with gravity because it would be very time consuming to do the astrometric monitoring of many stars. But if you know that there are candidates around star and you just want to determine their location, then maybe a couple of high precision astrometric points with gravity could help you to determine the reflex motion and thus the location of the planet. Another way is to maybe dig into the Gaia data. Gaia has been observing the stars for a few years. So in principle, it may be possible to dig out the acceleration, not just the proper motion, but the acceleration of the star from those data. And if you can do this, then you directly have an estimate of the direction of the gravitational force and so of the direction of the planets. So all of these are ideas which could be used to determine the position of Gaia candidates for following up with something like gravity. Now, and this is my last slide. I think one of the big questions which remains is what are the perspectives really for doing something like this? I mean, how many planets can we expect to put in the mass luminosity diagram using a combination like this? And there was a recent study which has been published by Wallace and colleagues trying to answer this question. So basically what they did is they looked at the stars from the known young associations. They generated a population of planets around those stars using, I believe, a core accretion model. And then they asked the question, so on those planets, how many would be detectable using Gaia astrometry, and how many would be detectable using direct imaging or gravity or possible other instruments? And their idea was to look at the overlap between the two. So how many planets would be detectable with both methods? And their answer can be either exciting or disappointing, depending if you were previously pessimistic or optimistic, I suppose. It's something around 10, maybe 15 planets, which is not a lot and certainly not enough for any significant statistical result using the mass luminosity diagram. But if you look at the numbers, it seems that the bottleneck in this is actually not really the Gaia astrometry, but it's probably more the direct imaging capabilities. And as Anne-Marie explained, there are a number of ideas to improve those capabilities in the future. So with the ELTs, of course, gravity plus will also improve the interferometric capabilities. Moving in the J-band is also an idea to increase the capabilities of the instrument at small separation. So that's one way to improve the number of planets that you can detect with both methods. The other way, which I think could be interesting to study, is, so this study was limited to stars of known young associations because those are the stars we know are young. but a star doesn't need to be a member of those associations to be young. So I think that it will also be interesting to try to look whether or not it could be feasible to have a more comprehensive catalog of young stars with Gaia candidate planets to have more targets on which to make those observations. But I have absolutely no idea of how this could be done. It's just an idea. And I think I will end with this. Thank you for your attention.
Thanks very much. Okay, just a note, if you have questions, participants, please pop them in the Q&A. We'll try to answer them either by text or via live. But let's move on to our last summary talk. Again, remember, longer versions of these talks are available online for the session, which will be by Andrew Mann.
All right, that coming through okay? Okay, great. So this is a good setup, actually. You've heard a lot about sort of the scientific motivations for detecting young planets. So I can focus mostly on the methodology. And as was said before, this is just a short version of the longer talk. So this is the kind of data set we're used to looking at for transiting planets in general. This is a light curve, flux versus time. And what I'm showing here are just two sort of two older planets, i.e. are two older systems with planets around them. These are with Kepler and the kind of data set we expect. And especially for the blue one, if you look closely, you see there's some stellar variability. There's some rotation, spots on the surface of the star. And if you look really closely and you have better eyesight than I do, you can probably see there's a handful of sort of low scattered points. Those are actually transits. Those are real transiting planets. You can see this is the beauty of the precision of Kepler, K2, and test data. You can spot very small transits even by eye because the data is so precise. The challenge with this comes for young stars because the stellar variability is so much larger. It looks something like this. So I have selected these two younger systems to show, light curves from younger stars, to show not because they're atypically bad, but actually because they're atypically good. These have transiting planets around them, and we tend to find transiting planets around the quietest stars. So these have something like, a couple percent variability, and but we have some where it's more like 5 or 10% variability. And you can see things like flares in the data. In fact, I've cut some off with the plot scale here. The transits you're looking for are small. You're often looking for signals that are 0.1% or 0.01%. And so you're trying to detect a signal that's something like 2 orders of magnitude smaller than the dominant signal, which is the signal from the star. It's kind of the same sort of stuff we were hearing about with radial velocity before. How do you deal with stellar variation? And to add on to this complexity, light curves show really complicated morphology for young stars. These are things like differential rotation, spots disappearing and reappearing on the surface of the star. And so even over sort of just a few week window or a few month window, you see really complex variations in these light curves, things that are difficult to model explicitly. So instead, the treatment here to try and detect the planet is something more flexible. And sort of the most common method falls under this broad category of things we call local filtering, or like a high pass filter. And there's a bunch of different techniques that fall under this window, but just to sort of give you a feel for how they all roughly work, you pick some window. This is some toy caricature of a light curve. You pick some window, and then you fit the light curve in that small region, right? You say it could be something as simple as median filter or a polynomial or spline, something more complicated. And then you repeat that process over the whole light curve, building up an empirical model effectively of the stellar variation. And simple versions of this method work actually extraordinarily well in a large number of cases. But they also fail a lot too. There's a lot of specific situations where these fail. And what I want to highlight here is sort of a situation where it works and a situation where it fails. These are two light curves here. I'm just showing a small section of the total light curve to focus on the transits. And again, you might see this transit by eye, but this one's a little harder to see by eye. And again, over the whole light curve, there'll be many transits. So you can stack them up and gain some signal noise. And when you look at something like this, you probably think, this one's pretty easy to detect. It's quite deep. It's a rather large signal. And you probably think this is sort of the harder one to detect. But I'd actually claim that it's the opposite. And the reason is that for the bottom light curve, the stellar variation works on extremely different timescales from the transit. So you're looking for this weak signal, but it's very short. And the stellar variability is a long period signal. Whereas on the top, this light curve works on very similar timescales, i.e. the transit duration, i.e. the length of this here, is similar to the stellar variation. And this is the kind of problem we deal with a lot with young star light curves, that the timescales involved become complicated. And you can see how problematic this becomes with this short little video here. This is the full light curve of what I just showed you, the top light curve. This is the full data from tests. And what I've done here in the bottom left is I've run a BLS periodogram. This is a common technique for detecting transit-like periodic signals. And I have the transit here in the bottom right, but in the bottom left, I've marked where the rotation period is of the star and the planet period. And what I'm going to do here is, as the video goes through, I'm going to sort of flatten this light curve using a detrending algorithm. And what you'll see is the stellar rotation signal gets weaker. And what's supposed to happen is the planet signal is supposed to sort of become more powerful relative to the total signal as you do this. But the problem with this particular curve, this would work well in a lot of systems, but it doesn't work well here because of this timescale problem. What's happening, you can see it in the bottom right, as soon as you've removed the stellar variability, you've also removed the transit. And there isn't really any simple way around this once you're working on similar timescales, at least not for these simple filtering tools. So there are lots of other methods, things like Gaussian process modeling. You can come up with physical models. These have various advantages and disadvantages, and I talk about some of those in the recorded talk, and I encourage you to look at that. What I want to focus on instead is the method that we've used. This is for our young planet search. And the main one we use is this thing we call the notch filter. And it works just like this sort of local variability filtering. You're still picking some window over which you're correcting for the light curve variability. The only difference is we're adding in a little trapezoidal notch, i.e. something we think that looks like a planet in there. And this has two advantages. One is that it prevents you from biasing your detrending. So normally you can see with the green dashed line here, what would happen is if you did a detrending and there was a transit there, it would be biased downward by the presence of the transit. And the other thing is that this lets you choose a very aggressive detrending algorithm that would normally remove planets, and you don't have to worry about removing them. And I'll just show you a quick video of how this works. This is the notch running through a light curve from a 10 million year old system. And as it goes through, it'll go slowly at first, and then it'll speed up. You can see the notch sort of activates on all sorts of things that actually aren't transiting planets. Some of them are real and some of them aren't. That's intentional. The goal here is just to be aggressive, but make sure the planets always survive this detrending thing. And you can sort of see the effect here. You see, some flares and things survive from outlier removal. You see there's actually a real transit present in that data, but there's also a bunch of junk. And what we sort of found is that's fine. You don't have to worry about too much about false positives, because what happens is when you detrend using something like notch, and you do get these low points that you might think are transits, but they don't phase to any constant period. And on inspection, they're clearly not transits. And in fact, the same thing is happening over here on the right, which is a system with a very clear planet. There's something that phases up to a Keplerian period, something periodic, something we expect from a planet signal, from a transit signal. There's also a whole bunch of other things that the notch is clearly activated on that are not transits, but they don't phase to anything. These are very easy to remove, even algorithmically. We don't even have to inspect these, which is advantageous for a bunch of reasons. And so this has been extremely successful. This is sort of the method, our go-to method now. We have a couple others, low-core, which is the other one I talk about in the long version of this talk, but notch has been sort of the most successful. And sort of just, the quick version summary of this, that effectively what's happened over the last 5 or 6 years, we've gone from having effectively 0 or 1 young transiting planets, and now we have something like 30 to 40. And a lot of this is driven by Kepler K2 tests, new mission data. That's really been the big driver, but also these sort of new techniques for data filtering. And a lot of these were found with sort of the simple case I showed earlier, just some local filtering, something like a median filter or some smooth detrending technique. But what we really like about these, about the notch filter and then this other one, low core, is it's the only one that recovers them all very consistently, which is important for doing statistics. You want to understand your completeness of your pipeline so that you know how many, for every planet you find, how many you missed, so to speak. And this has worked across TESS, K2, and Kepler now, mission data. We've run on all of them. And very advantageous, the pipeline is actually online, the notch filter. You can go to GitHub, you can download it. They're not terribly well documented notebooks, but they're there for running them, and you're welcome to use those. We'll try to keep those up to date. And it's allowed us to build up a really big sample of young planets over the last few years. And I think I'll stop there. We might have some time for discussion.
Yes. Thanks for another great talk. So 4 really nice talks. We have a little bit of time for questions. So I think what we're going to do is we're going to start and go through one question from the chat per speaker, starting basically moving backwards in time. So let's start with a question then for Andrew. So we have a voted question. Could you please explain the notch filter more? And related to that, how do you assign the width of window for fitting the curve? Is there a fixed setting? What things should we be concerned with when we assign them?
Yeah, so as for the first part of the question, just the notch filter, effectively you are just doing like a local detrending with a transit shape in there. And as it's moving through, the sort of part I skipped over in the interest of time is that the notch can sort of activate at any time, and if it sees anything vaguely transity, and so this is why it activates on lots and lots of things. So it's very generous. There's some calculation for when it should activate, which is based on just a goodness of bit test, like it's a Bayesian information criterion, and in fact the BIC values that it spews out at the end are useful for vetting later. It turns out large significances often can help us find like single transiting systems. Okay, the question about the window. Basically what we did is we ran a whole bunch of planets we had already found and tuned up the windows until we found one that worked pretty well. That being said, one of the advantages of this pipeline is it's fast. It can be run extremely quickly, even on just like my laptop in front of me. And so in fact, what we actually do is we run a whole bunch of different windows. Half a day is a good place to start, but reality is you're going to tweak it based on the star. So often we have some prior information about the rotation period of the star. We tune it to that. So faster rotating stars make it a little shorter, slow rotating make it a little longer. But again, you can run it on many, many settings as an advantage of a fast pipeline.
Great. Okay.